Okay, testing. Is the joke working? I tried to make a joke, but I don't know if I succeeded or failed. Oh, shoot. Wow, feels like I haven't been on stream for ages. I keep failing with... I got it. Now I see what happened. Okay. Why is her mouth not moving? Yeah, no, I'm failing spectacularly right now. Let's try and fix this. Be right back. Okay. Fixed. We did it. Okay. So the joke is that my hijab is see-through. Is it working? Alright. Are we still live, or did I mess that one up as well? Okay, we gotta be still live. Alright. Let's get to it then. I'm still wearing Halloween style themed things, so that will probably be old soon. God, I think the style of my... Oh, speak loudly? Is my voice really low? Hello, by the way, hi. I was just checking to see if the chat was working. Thank you for putting something in the chat. How are you? I'm just checking if the hijab is looking odd or not. Oh, thanks. Okay, got it. Because it's supposed to be see-through, and it sort of is, but it sort of also looks white, and I don't know if it's annoying or not. Anyway, shall we do a recap of what we're doing and why are we even here? So, welcome to today's stream on... Okay, it looks like my face is floating. I like it. Introduction to Machine Learning for Coders, an online course on the fast.ai platform that's taught by Jeremy Howard, and it has here, it says that, and it used to be a master's course at University of San Francisco. 8 hours. If you study 8 hours a week for 12 weeks, you'll be able to complete it. And I think there are 12 videos that you can follow up on. We're currently on video number 9, if you can believe that. So yeah, good on us for consistency. Video number, like lesson, not video. Lesson number 9 takes us through regularization, learning rate, and NLP. Yeah. I think we were at the learning rate when I left it last time. So, yes. I think I'm just gonna go to the video. I do remember myself not thinking the past like almost 5 minutes of this video because I couldn't really understand what was going on. So I think I'm gonna go back.
Could you lift things?
It's going 2 or 3 layers deep.
So if I wanted to go deeper, I would just do...
Okay, so this is just the training of linear layer and a softmax layer, and then he's adding ReLU layers, which links the layers. I remember that part. Okay.
That. Okay, that's a now 2 hidden layer network.
So I think I'd heard you said that there are a couple of different activation functions like that rectified linear unit. What are some examples, and why would you use each?
Yeah, great question. So basically, like, as you add like more linear layers, you kind of got your input comes in and you put it through a linear layer and then a non-linear layer, linear layer, non-linear layer. Linear layer, and then the final non-linear layer. The final non-linear layer, as we've discussed, if it's a multi-category classification, but you only ever pick one of them, you would use
multi-category classification. Okay, we're choosing the type of animal, let's say, for example, and we're choosing which animal it is at the end. Let's see.
Softmax. If it's a binary classification or a multi-label classification where you're predicting multiple things, you would use sigmoid.
Wait. If it's binary or multi-labeled, we use sigmoid? Is that what he said?
Classification where you're predicting multiple things, you would use sigmoid. If it's a regression, you would often have nothing at all, right? Although we learned in last night's DL course where sometimes you can use sigmoid there as well.
Okay.
So they're basically the options, main options for the final layer. For the hidden layers, you pretty much always use
ReLU?
ReLU. Right, but there is another one you can pick, which is kind of interesting, which is called leaky ReLU, and it looks like this. And basically, if it's above 0, it's y equals x, and if it's below 0, it's like y equals 0.1x. Okay, so it's very similar to ReLU, but it's rather than being equal to 0 under x, it's like something close to that. So they're the main two, ReLU and leaky ReLU. There are various others, but they're kind of like things that just look very close to that. So for example,
and like this is 2018, right? I'm curious what's different, or if I take their deep learning course, because like this is what you use if you want a practical or even competition, right? Okay.
For example, there's something called ELU, which is quite popular, but like the details don't matter too much, honestly. Like like ELU is something that looks like this, but it's slightly more curvy in the middle. And it's kind of like, it's not generally something that you so much pick based on the data set. It's more like over time we just find better activation functions. So 2 or 3 years ago, everybody used ReLU. You know, a year ago, pretty much everybody used leaky ReLU. Today, I guess probably most people are starting to move towards ELU. But honestly, the choice of activation function doesn't matter terribly much, actually. And, you know, people have actually showed that you can use like pretty arbitrary nonlinear activation functions, like even a sine wave. And it still works. Okay.
Oh, that scared me.
So although what we're going to do today is showing how to create this network with no hidden layers, to turn it into that network, which is 96%-ish accurate, it will be trivial, right? And in fact, it's something you should probably try and do during the week, right? Is to create that version.
We already tried the linear part. I don't know about the ReLU, but adding another, just calling the linear function again, I don't think that would be a problem at all, actually.
Okay, so now that we've got something where we can take our network, pass in our variable, and get back some predictions, that's basically all that happened when we called fit. So we're going to see how that approach can be used to create this stochastic gradient descent. One thing to note is that to turn the predicted probabilities into a predicted, like which digit is it, we would need to use argmax. Unfortunately, PyTorch doesn't call it argmax. Instead, PyTorch just calls it max, and max returns two things. It returns the actual max across this axis, so this is across the columns, right? And the second thing it returns is the index of that maximum, right? So the equivalent of argmax is to call max and then get the first indexed thing. Okay, so there's our predictions.
Right.
If this was in NumPy, we would instead use np.argmax. Okay. All right.
All right.
So here are the predictions from our hand-created logistic regression, and in this case...
Wait, is it more accurate than the last time? Is everything correct? Whoa. It's all correct. 93658436. That's amazing.
Looks like we got all but one correct.
Oh, where's the one? Hold up. Oh, this is supposed to be 3, not 5. Got it. I didn't, my mind didn't register that one.
So the next thing we're going to try and get rid of in terms of using libraries is we'll try to avoid using the matrix multiplication operator, and instead we're going to try and write that by hand.
Which matrix multiplication operator?
So this next part, we're going to learn about something which kind of seems, it's going to seem like a minor little kind of programming idea. But actually it's going to turn out that, at least in my opinion, it's the most important programming concept that we'll teach in this course, and
Really?
it's possibly the most important programming kind of concept in all of the things you need to build machine learning algorithms.
Whoa, he's hyping it up real good. I have to focus. Okay, I'm going to focus.
And it's the idea of broadcasting. And the idea I will show by example. If we create an array of 10, 6, neg 4 and an array of 2, 8, 7, and then add the two together, it adds each of the components of those two arrays in turn.
Okay.
We call that element-wise.
Mm-hmm.
So in other words, we didn't have to write a loop, right? Back in the old days, we would have to have looped through each one and added them and then concatenated them together. We don't
Okay. Back in the old days? Before Python, or?
have to do that today. It happens for us automatically.
Mm.
So in NumPy, we automatically get element-wise operations.
NumPy. Yeah, normal Python you'd still need a loop. Okay, NumPy is nice.
We can do the same thing with PyTorch.
Hmm?
So in fast.ai, we just add a little capital T to turn something into a PyTorch tensor, right? And if we add those together, exactly the same thing, right? So element-wise operations are pretty standard in these kinds of libraries.
Okay.
It's interesting not just because we don't have to write the for loop, right? But it's actually much more interesting because of the performance things that are happening here. The first is, if we were doing a for loop, right? If we were doing a for loop, that would happen in Python, right? Even when you use PyTorch, it still does the for loop in Python. It has no way of like optimizing a for loop.
Okay.
And so a for loop in Python is something like 10,000 times slower than in C.
Wow.
So that's your first problem. I can't remember, it's like 1,000 or 10,000. The second problem then is that you don't just want it to be optimized in C, but you want C to take advantage of the thing that all of your CPUs do, which is something called SIMD, single.
I don't know what SIMD is, but are we going to use Python? Let's see.
Instruction, multiple data, which is your CPU is capable of taking 8 things at a time, right, in a vector, and adding them up to another vector with 8 things in a single CPU instruction, right? So if you can take advantage of SIMD, you're immediately 8 times faster. It depends on how big the data type is. It might be 4,
Okay.
or it might be 8. The other thing that you've got in your computer is you've got multiple processors, multiple cores. So you've probably got, like if this is happening on one core, you've probably got about 4 of those. Okay, so if you're using SIMD, you're 8 times faster. If you can use multiple cores, then you're 32 times faster. And then if you're doing that in C, you might be something like 1,000 times faster, right? And so the nice thing is that when we do that, it's taking advantage of all of these things. Okay?
Okay.
Better still, if you do it in PyTorch and your data was created with .CUDA to stick it on the GPU, then your GPU can do about 10,000 things at a time, right? So that'll be another 100 times faster than C, right? So this is critical to getting good performance, is you have to learn how to write loopless code by taking advantage of these element-wise operations. And like it's a lot more than just plus. I could also use less than, right? And that's going to return 0, 1, 1. Or if we go back to NumPy, false, true, true. And so you can kind of use this to do all kinds of things without looping. So for example, I could now multiply that by A, and here are all of the values of A, as long as they're less than B. Or we could take the mean. This is the percentage of values in A that are less than B.
Whoa.
Right? So like there's a lot of stuff you can do with this simple.
That's a lot of stuff. That can make your, like, you can just make it like sometimes in normal, I haven't used NumPy, obviously you can tell, but when you want to do something and you have to be stuck on the how, then you get slowed down. But when you just do the thing, then you're stuck on, not stuck on, but you're now in the how to optimize it, what to do next, instead of why is the thing that I wanted not working. So that helps a lot.
Idea. But to take it further, right, to take it further than just this element-wise operation, we're going to have to go the next step to something called broadcasting. So let's take a 5-minute break, come back at 2:17, and we'll talk about broadcasting.
I'm still here.
So, broadcasting. This is the...
What's broadcasting? Oh, okay, so we weren't talking about broadcasting till now. I suppose I'm pretty good at broadcasting. I can stream on Twitch or YouTube.
The definition from the NumPy documentation of broadcasting. And I'm going to come back to it in a moment rather than reading it now. But let's start by looking at an example of broadcasting. So A is a array with one dimension, also known as a rank 1 tensor.
Yep,
also
rank
known
1
as a vector.
tensor. And a vector, yes.
We can say A greater than 0. So here we have a rank 1 tensor, right, and a rank 0 tensor. Right? A rank 0 tensor
It's just a constant, just a number.
is also called a scalar.
Oh yeah.
Rank 1
Scalar values, yes.
tensor is also called a vector. And we've got an operation between the two.
It will use the scalar on every element of the vector.
Right? Now you've probably done it 1,000 times without even noticing that's kind of weird, right? That you've got these things of different ranks and different sizes. So what is it actually doing, right? Well, what it's actually doing is it's taking that scalar and copying it here, 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 right? And then it's actually going element-wise. 10 is greater than 0. 6 is greater than 0. Minus 4 is greater than 0. Even giving us back the 3 answers, right? And that's called broadcasting. Broadcasting means copying one
Element to other elements?
or more axes of my tensor to allow it to be the same shape as the other tensor. It doesn't...
I think I understood it, but like the way he said it, I didn't understand it.
really copy it though. What it actually does is it stores this kind of internal indicator that says pretend that this is a vector of 3 zeros, but it actually just like rather than kind of going to the next row or going to the next scalar, it goes back to where it came from. If you're interested in learning about this specific...
I don't know if that's a sketch or not, but like I'm guessing there's a Mr. Bean sketch where he acts as if he's the next person multiple times. So that's what it reminds me of. And I don't know if it even exists or not.
They set the stride on that axis to be 0. That's a minor advanced concept for those who are curious. So we could do A plus 1, right? It's going to broadcast the scalar 1 to be 1, 1, 1, and then do element-wise addition. We could do the same with a matrix, right? Here's our matrix. 2 times the matrix is going to broadcast 2 to be 2, 2, 2, 2, 2, 2, 2, 2, 2, and then do element-wise multiplication.
Right.
Right? So that's our kind of most simple version of broadcasting. So here's a slightly more complex version of broadcasting. Here's an array called C.
An array and a matrix. Let's see what happens.
Right, so this is a rank 1 tensor. And here's our matrix M from before, our rank 2 tensor. We can add M plus C. Right? So what's going on here? 1, 2, 3, 4, 5, 6.
I think it just assume the array. Where's our array? The 10, 20, 30 is there 3 times, just like how this here. I think that's what happens, right?
7, 8, 9. That's M. Right? And then C. 10, 20, 30. You can see that what it's done is to add that to each row. Right? 11, 22, 33. 14, 25, 36. And so we can kind of figure it seems to have done the same kind of idea as broadcasting a scalar. It's like made copies of it.
Basically. Depending on the shape, it will try to make copies of it. Because like this is a 3x3. But what if it was like a 2x4? Then what happens?
And then it treats those
As one matrix, rank 2 tensor.
as if it's a rank 2 matrix. And now we can do element-wise addition. Does that make sense? Okay. Now that's, yes, can you pass that, Devon, over there? Thank you.
So, as it's like, by looking at this example, it like copies it down, making new rows. So how would we want to do it if we wanted to get new columns?
I'm so glad you asked. So instead, we would do this. 10, 20, 30. All right, and then copy that. 10, 20, 30.
Yeah.
10, 20,
But what if
30.
it conflicts with the shape, though?
And now treat that as our matrix. So to get NumPy to do that, we need to not pass in a vector, but to pass in a matrix with one column, right? A rank 2 tensor. Right? So basically, it turns out that NumPy is going to think of a rank 1 tensor for these purposes as if it was a rank 2 tensor, which represents a row. Right? So in other words, that it is 1 by 3. Right? So we want to create a tensor which is 3 by 1. There's a couple of ways to do that. One is to use np.expandIms. And if you then pass in this argument, it says, please insert a length 1 axis here, please. So in our case, we want to turn it into a 3 by 1. So if we said expandim c, 1, okay, so if we say expandim c, 1, it changes the shape to 3, 1. So if we look at what that looks like a column. Okay.
Ah, okay. That's cool.
So if we now go that plus m, you can see it's doing exactly what we hoped it would do. Right, which is to add 10, 20, 30 to the column. 10, 20, 30 to the column, 10, 20, 30 to the column. Okay. Now, because the location of a unit axis turns out to be so important, it's really helpful to kind of experiment with creating these extra unit axes and know how to do it easily. And np.expandims isn't, in my opinion, the easiest way to do this. The easiest way
Is?
The easiest way is to index into the tensor with a special index none. And what none does is it creates a new axis in that location of length 1, right?
That's cool. How can we do the expand dim one?
So this is going to add a new axis at the start of length 1. This is going to add a new axis at the end of length 1. Or why not do both?
Whoa.
Right? So if you think about it, like a tensor which has like 3 things in it could be of any rank you like, right? You can just add unit axes all over the place. And so that way we can kind of decide how we want our broadcasting to work. So there's a pretty convenient thing in NumPy called broadcast2. And what that does is it takes our vector and broadcasts it to that shape and shows us what that would look like, right? So if you're ever like unsure of what's going on in some broadcasting operation, you can say broadcast2. And so for example here we could say, like rather than 3,3, we could say m.shape, right? And see exactly what's going to happen. And so that's what's going to happen before we add it to m, right?
Okay.
So if we said turn it into a column, that's what that looks like. Make sense? Yeah.
Sorta.
So that's kind of like the intuitive definition of broadcasting. And so now hopefully we can go back to that NumPy documentation and understand what it means, right? Broadcasting describes how NumPy is going to treat arrays of different shapes when we do some operation, right? The smaller array is broadcast across the larger array. By smaller array, they mean lower rank tensor, basically. Broadcast across the higher rank tensor, so they have compatible shapes. It vectorizes array operations. So vectorizing generally means like using SIMD and stuff like that, so that multiple things happen at the same time. All the looping occurs in C, but it doesn't actually make needless copies of data. It kind of just acts as if it had. Right? So there's our definition. Now in deep learning, you very often deal with tensors of rank 4 or more.
Right.
And you very often...
And it's really annoying to imagine. Like, my mind's eye just becomes blind. Not that that's what we were talking about.
Combine them with tensors of rank 1 or 2, and trying to just rely on intuition to do that correctly is nearly impossible. So you really need to know the rules.
Rules?
So here are the rules. Okay, here's m.shape, here's c.shape. So the rule are that we're going to compare the shapes of our 2 tensors element-wise. We're going to look at one at a time. And we're going to start at the end, right? So look at the trailing dimensions and then go towards the front, okay? And so 2 dimensions are going to be compatible when one of these 2 things is true, right? So let's check, right? We've got...
it's nm and nm, and we get a nm. Why do I remember that? Like the size, if it's row column, you get the row of the first, the column of the second, if the shapes are different. Am I right? Am I remembering correctly?
Are M and C compatible? M is 3, 3. C is 3. Right? So we're going to start at the end, trailing dimensions first, and check. Are they compatible? They're compatible if the dimensions are equal. Okay, so these ones are equal, so they're compatible. Right. All right, let's go to the next one. Uh-oh, we're missing. Right? C is missing something.
You'll be fine.
So what happens if something is missing is we insert a 1. Okay, that's the rule. Right? And so let's now check. Are these compatible? One of them is 1. Yes, they're compatible. Okay? So now you can see why it is that NumPy treats the one-dimensional array as if it is a rank 2 tensor, which is representing a row. It's because we're basically inserting a 1 at the front.
Right.
Okay? So that's the rule. So for example, this is something that you very commonly have to do, which is you start with like an image of like 256 pixels by 256 pixels by 3 channels, and you want to subtract the mean of each channel, right? So you've got 256 by 256 by 3, and you want to subtract something of length 3, right? So yeah, you can do that, absolutely, because 3 and 3 are compatible because they're the same, right? 256 and empty is compatible because it's going to insert a 1. 256 and empty is compatible because it's going to insert a 1, right? So you're going to end up with, this is going to be broadcast over all of this axis, and then that whole thing will be broadcast over this axis, and so we'll end up with a 256 by 256 by 3.
Oh, you're showing me the result at the end. I, for some reason, thought image and scale, the 3 and 2, and the 3. I thought we were like doing it with 3 different tensors, but it's a 3-dimension tensor and the result. Okay, my focus is getting away.
Effective tensor here, right? So interestingly, like, very few people in the data science or machine learning communities understand broadcasting, and the vast majority of the time, for example, when I see people doing pre-processing for computer vision, like subtracting the mean, they always write loops over the channels, right? And I kind of think like, it's like so handy to not have to do that, and it's often so much faster to not have to do that. So if you get good at broadcasting, you'll have this like super useful skill that very, very few people have.
Okay.
And like it's an ancient skill, you know. it goes all the way back to the days of APL. So APL was from the,
I thought by ancient he meant like there are methods that have been used since, like, you know, like algorithms were invented. But now ancient means beginning of the programming, I guess.
late 50s.
Oh, okay, that's pretty ancient because technically computers were just punching cards.
Stands for programming language. And Kenneth Iverson wrote this paper called Notation as a Tool for Thought, in which he proposed a new math notation. And he proposed that if we use this new math notation, it gives us new tools for thought and allows us to think things we couldn't before.
That's
And
so
one of
cool.
his ideas was broadcasting, not as a computer programming tool, but as a piece of math notation.
Wow. Different style, I mean, new ways of thinking. This is cool.
And so he ended up implementing this notation as a tool for thought as a programming language called APL. And his son has gone on to further develop that into a piece of software called J, which is basically what you get when you put 60 years of very smart people working on this idea. And with this programming language, you can express very complex mathematical ideas, often just with a line of code or two. And so, I mean, it's great that we have J, but it's even greater that these ideas have found their ways into the languages we all use.
They have transcended its first language and now they're here. That's cool.
Use, like in Python, the NumPy and PyTorch libraries. Right? These are not just little kind of niche ideas. These are like fundamental ways to think about math and to do programming. Like, let me give an example of like this kind of notation as a tool for thought. let's look. Here we've got C, right? Here we've got C, none, right? Notice this is now at 2 square brackets, right? So this is kind of like a 1 row rank 2 tensor. Here it is as a column.
Okay.
So what is... didn't mean to do some examples.
10 times 20 times 30. I mean, technically it's supposed to be not compatible, am I right?
Okay, what's that going to do?
Because one of them is 3 by 1, the other one is 1 by 3. But then we could do, because like the way I remember it, the result is a 3 by 3 matrix of 10 times 10, and then 10 times 20, 10 times 30, and then 20 times 10, 20 times 20, 20 times 30, and then 30 all the way. I think that's how I remember it.
Have a think about it.
Oh, that's what I was doing.
Does anybody want to have a go? Can even talk through your thinking? Okay, can we pass the... Jack, just over there. Thank you.
Kind of outer product.
Yes, absolutely. So take us through your thinking. How's that going to work?
The diagonal elements can be directly visualized from the squares. 10 cross 10, 20 cross 20, and 30 cross 30. And if we multiply the first row with this column, we can get the first row of the matrix. So finally we'll get a 3 cross 3 matrix.
Yeah.
Yay.
And so to think of this in terms of like those broadcasting rules, we're basically taking this column, right, which is of rank 3, 1, right, and this kind of row, sorry, that's dimension 3, 1, and this row which is of dimension 1, 3, right, and so to make these compatible with our broadcasting rules, right, this one here has to be duplicated 3 times because it needs to match this.
Right.
Okay, and now this one's going to have to be duplicated 3 times to match this.
Yep. That's not how I studied.
And so now I've got 2 matrices to do an element-wise product of. And
The way I learned this was just that the outcome is first row, last column. But I like the broadcasting rule. I like it better.
so, as you say, there is our outer product. Right? Now, the interesting thing here is that suddenly, now that this is not a special mathematical case, but just a specific version of the general idea of broadcasting, we can do like an outer plus, or we can do an outer greater than, right? Or whatever, right? So it's suddenly we've kind of got this concept that we can use to build new ideas, and then we can start to experiment with those new ideas. And so, you know, interestingly, NumPy actually uses this sometimes. For example, if you want to create a grid, this is how NumPy does it, right? Actually, this is kind of the, sorry, let me show you this way.
Make grid?
If you want to create a grid, this is how NumPy does it. It actually returns 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4. One is a column, one is a row. So we could say like, okay, that's X grid, Y grid. And now you could do something like, well, I mean, we could obviously go
Sum them up.
like that, right? And so suddenly we've expanded that out into a grid, right?
Right.
And so, yeah, it's kind of interesting how, like, some of
This looks really cool. 1, 2, 3, 4, 5 till 8.
these, like, simple little concepts kind of get built on and built on and built on. So if you lose something like APL or J, it's this whole environment of layers and layers and layers of this. We don't have such a deep environment in NumPy, but you can certainly see these ideas of like broadcasting coming through in simple things like how do we create a grid in NumPy. So that's broadcasting. And so what we can do with this now is use this to implement matrix multiplication ourselves.
Okay, that would be cool. But I think I'm out of it for today. Oh, I've been here 15 minutes. That's pretty good. I'm proud of myself for making it this far. Okay. Hello. Okay. Oh, why is it so slow? What happened? Why are you reacting as if it's your fault? Wake up. Yeah, okay. She's reacting really slowly. I don't know why. But I wanted to say, past week I've been pretty sick, so I wasn't like on my deathbed sick, obviously, but I don't know if you can tell from my voice, it's still not fully recovered. I had a sore throat and all that, so it was not fun. Talking was absolutely not fun. And if you can't tell, streaming is a lot of talking. So I apologize for being away. Forgive me. And by the way, I have this staring at me, this follower goal. I had it at 75 and that got crushed was it last week, I think? So I'm gonna update it, and it's a bit scary, but I think I can set the goal to like, where's follower goal? Testing it. Goal, there it is. Nope, not that. Follow. But where can I set the follower goal? The other day I saw it, but then what's happening? Someone help me. I don't know what I'm doing. Yeah, no, I think I'm lost. I thought I could do it, but now I'm super lost. So literally I found it the other day. Yeah. Oh, there it is. Start new goal. Whew. Okay. So, they're recommending me to set my goal to 90, but I mean, it's only fair for me to do 100. I don't know. I don't know if we'll get there ever. So I'm going to start the goal. There will probably be a... Yay, she started a goal. Sort of. Yep. Hi. Hi notification. Yep. I did that. That was me. So let's see if that gets anywhere. Doesn't really matter that much because it would be cool, but our main point here is learning, not running for goals. Okay. I was supposed to be here until no, this is good. I can leave now. Time is really good. Today, the thing that's currently in my brain is the broadcasting one. A lot of tensors and just working with tensors. Now I'm saying tensors instead of saying arrays and matrices, so I've gone up a bit. Yeah. Thank you. Sorry my voice is not good today. And see you tomorrow, inshallah. Yeah. With more of this. Okay. Gonna end the stream in 5, 4. Today's stream health is really good though. But I don't know why she's getting stuck. My mouse isn't stuck, but you are. Wake up. Okay. 3, 2, and 1. Thank you for stopping by. See you next time.